All right, here are the solutions to quiz 6, the one we took right before spring break, or the first spring break. The There are a couple of small things on this. I know you worked together on it, so I try to make some notes and some very small deductions for things where you're not paying attention to the details. And mostly it's when the notation is actually there to guide you, and some people are misusing it, which I think might be causing some misunderstanding, or it may just be that that you're just sort of in a hurry and writing equal when you don't really mean equal or whatever. So let me just talk a little bit about the details about what I wrote on your papers, and also go through the correct solutions here. So the first problem says find the sum of the first 5 terms of this series. And so just a notational note, when we talk about the AKs here, that's going to be the formula for the terms that we're using. And so our textbook would say that the AKs are just these positive terms, and then they would say that the alternating part is coming from the -1 to the k. It's not wrong to decide your AKs mean the whole thing. And the only reason I'm pointing this out is because I want to make sure that everybody's okay with the fact that some of the statements that they use in the book are going to be based on the notation that they think you're using, and if you're using something else, then you'll have to kind of adjust. The only difference between these is whether we're keeping the alternating -1 plus 1 as part of the AK definition or not. So it doesn't really make any difference, but it does impact the way you talk about things. So when we want to add together the first 5 terms, I'm going to stick to the way the book is doing it, just so that I get the formulas and theorems the same way they wrote them. But I'll tell you how that translates to the other one in a second. So if I'm adding up the first few terms, notice that here the k's start with k equals 0. So that means that I'm going to have a0 minus a1 plus a2 minus a3 plus a4. That would be 5 terms. The notation that they use for that in our textbook is they call that S4. They always use the subscript for the partial sum notation. In the partial sum notation, the subscript here matches the largest value that you've included. So it's not S5 just because you added 5 terms. The reason that matters is that the theorem for the error bound down here is going to say that the error that you get when you're using the SN estimate is no more than the value of the very next term. And so so the very next term here would be the very next term from the series would be the A5 term. That would be the very next thing. And so I don't want this to accidentally become A6. Okay. So anyway, so for this to make sense, this is the convention that you have to use. Okay. So the value of this, and of course, if you're living in the world where this is your way you've defined it, then in your world you're just adding up the A's that you have, but you're still adding up to A4, and so you'd still want to refer to that as S4. Okay, so so there was no issue with getting the right answer for this. Obviously, we were working together and using the computers, but I'll write it down here anyway so I can refer back to it. So 0.606771. I'm just going to keep all those decimal places because I don't know how close this is going to be. So for the remainder, let me just again write down some of these terms. So the exact S, the exact value of the infinite series, is going to be this thing forever. I won't really write it down forever, but it goes like that. So notationally, remember this part, if we call this part S4, like I said above, then all of this stuff would be considered R4. So that's the remaining terms if you use S4 as your estimate. So if you cut off the infinite sum at S4, then R4 is how much is left over. So that means R4 is the exact good Lord, the exact error when you use S4 to estimate the infinite sum. So that's what R4 is. So R4 is the error. So this is representing the actual error that you make. The reason that we call these theorems upper bound theorems or bounding theorems on the error is because of this less than or equal to sign. So we're not going to be able to figure out what R4 is equal. So on your quiz paper, if you wrote R4 is equal to something, to some number, you're wrong. You don't know what R4 is. R4 is the exact value of the error. What the theorem tells us is that we can figure out how bad the error could be by using this theorem. The error bound theorem says that the absolute value of R4, that's how much error we could possibly make, is no more than, less than or equal to is no more than A5. So A5 is just literally this formula with k equals 5. So 1 over 2 to the 5th times 5 factorial, which is approximately 0.00026. So again, this is an upper bound on the error. This is the error. This is an upper bound on the error. So you shouldn't write R4 is equal to this. That's not true. But R4 is no more than this. That is true. And that's why the theorem has a less than or equal to sign. So try to keep that straight. This is the exact error, and this is the upper bound on the exact error. That's where, when you say upper bound, you're going to see an inequality sign like that. All right. Is it really not going to all move? Good grief. Hang on. Let me just get rid of this stuff so I can scroll. So number 3 is to expect our estimate to be larger or smaller than the actual value of the infinite series. This is something specific about alternating series. And so here's a graph. The graph here is, this is Sn on this axis, and these are n's. So this value is because S0 would be 1. This value is because S1 would be 1 minus, oh God help me, 1 minus a half. No. Yeah, 1 minus a half. Oh yeah, that's what it is. Okay, so, and so here, way over here, this is our, whatever that number was, 0.606771. Right, that was our S4. And see how it's above a 4. So that's what's happening there. The theorem tells us, the alternating series theorem tells us that that our partial sums alternate overestimating and underestimating the actual value of the series. Now that doesn't really start happening until your A's are decreasing. So there's a caveat to that, but in this case they always are. So so what that means is that the true value of the series can be seen from the consecutive estimates here. This one is too big. I can see that it's high. This one is too small. And I know it's too small because it's the next estimate. This one's too big because it's the next estimate. This one's too small because it's the next estimate. This one's too big. The next one would be too small. Okay. And so the real value then, the real limit of the series is going to be stuck in between these values. So whatever number is going in between all of these things is going to be your actual limit. And so because the partial sums alternate being too big or too small, all you have to do is look and see, if you look at two of them in a row, you'll know which one's which, because one's going to be bigger than the other. The larger one's going to be the one that's too big, and the next one's going to be going to be too small. You can tell that from the form of the partial sum by just seeing whether you're ending with a plus or a minus. So for us, S4 here was A0 minus A1 plus A2 minus A3 plus A4. The next partial sum would have been exactly all of that stuff minus A5. So you see that S5 has to be smaller than S4, right? It's the same thing, but you subtracted something at the end. And so since these consecutive partial sums have to be alternating too big and too small, I know S4 is too big and S5 is too small. So in other words, I know that the real answer is in between those two. And so however you want to say that is fine, but that's what I was trying to get at there, that we do know that, and it's still not going to scroll, is it? I can get rid of that too. All right, and so finally we're just checking to make sure that everything makes sense. So we do know in this case, or I do know in this case, that the real value of this series is the square root 1 over the square root of e, and we will be talking in our first week back about how I know stuff like that. 1 over e is approximately 0.606531. Let me just bring my other results down since I had to delete them. I get S4 was 0.606771. And so, so first of all, yeah, I can see that S4 is bigger than 1 over the square root of e, just by comparing those numbers. And secondly, I can see how big the difference is by just subtracting. Since S4 is the bigger one, I'll write that one first. So if I subtract these two, that's my actual error. That's going to be 0.00024. And then just note that number 2, our number 2 said the actual error should be less than 0.00026. That's what you had in number 2. And so you can see that that also is correct. So we were correct about which one was bigger, and when we look at the actual error, we can see that the actual error really was smaller than 0.00026, which is what the bound gave us. Just FYI, this would be R4, right? That's what R4 is. It's the actual error that you get if you use S4. The only reason that we can compute it in this problem is because I'm cheating and telling you what the infinite sum adds up to. In a lot of problems, we won't know what the actual value of the infinite series is, but we don't really need to if we can always give an error, an estimate, and know that our estimate is good to within whatever tolerance we need. Then we don't actually need exact answers to do our work.